Throughout this lesson, we are going to look at humidity. In particular, we will concentrate on the different states of water, how water changes between these states, and why the effects of these changes are important to meteorology. Water has three states or phases: the solid state called ice, the liquid phase simply called water, and the gaseous state called water vapor. One of the major impacts water has on our atmosphere is when it changes from one phase to another. During these changes, energy is transferred in different ways. This energy is known as latent heat. You may recall from the lesson on temperature, this is where heat is liberated as a substance changes state. So energy in the form of heat is either released or absorbed by the change of state. Let us see what happens when a substance changes state from solid to liquid, in other words, during melting. As we heat the solid, it will start to melt. Energy in the form of latent heat is absorbed from the surroundings and then stored in the liquid. Let us now examine the change of state from liquid to gas. This is known as evaporation. During evaporation, latent heat energy is absorbed from the surface and stored in the water vapor. We can experience this absorption of energy in our everyday lives. When we have moisture on our skin and it evaporates, our skin temperature falls. This is because heat is being removed from our bodies and absorbed into the water vapor. In fact, when we are too hot, our body will produce moisture on the skin called sweat. This is the body's way of controlling its temperature. Evaporation from a water surface will occur at any temperature above absolute zero, which is minus 273 degrees Celsius, but the rate of evaporation increases as the temperature increases. This is because at higher temperatures the molecular activity is greater and a change of state is more likely. However, there is only so much water vapor a unit volume of air can hold at any given temperature and pressure. This graph shows you how much water vapor can be held at any given temperature. You can plainly see that the higher the air temperature, the more water vapor that can be held in the air. When the air is completely full of water vapor and can hold no more, the air is said to be saturated. No more evaporation can take place because the air cannot hold any more water vapor. We have established that one way we can make air saturated is by adding water vapor to the air through the process of evaporation until the air is full of water vapor. However, there is another method to achieve saturation. You may recall from the previous scene that cold air cannot contain as much water vapor as warm air. So, if we have a parcel of air that is partially filled with water vapor and then cool it down, the air will eventually reach a point where it is holding as much water vapor as it can. Again, the air has become saturated. Further cooling will cause condensation and formation of cloud. Condensation is the reverse of evaporation. It is the phase change from vapor back to liquid. You will remember that the water vapor had a lot of stored latent heat. So when it then condenses and changes into water again, it releases this latent heat back to the surrounding air. As we have seen, condensation is said to occur when water vapor changes state into visible water, like dew, clouds and fog. But this process is actually quite complex. For condensation to occur, we need minute particles in the atmosphere for the water to form around. These are called condensation nuclei, and mainly consist of salt particles put into the atmosphere over the sea. There are other condensation nuclei, such as pollutants from industrial sources, forest fires, or volcanic eruptions. These help the condensation process and can aggravate cloud formations. The change of state of water from liquid to solid is known as freezing. When the temperature of water drops below 0 Celsius, it generally turns to ice. Remember from earlier in the lesson that this involves the release of latent heat. Here we can see the heat being given up to the surroundings during the freezing process. However, in the atmosphere, freezing usually requires the presence of particles. In this case, they are known as freezing nuclei. So as the temperature of the droplet falls, if there are particles in the water, the droplet will freeze. However, if they are not present, then when the temperature falls below 0, it will not freeze. In this state, the water droplets are known as supercooled water droplets. They are very important in aircraft icing. There are two other phase changes that we need to mention. These are less common in the atmosphere than condensation or evaporation, but nevertheless are important. When water goes straight from the solid to gas, we call it sublimation. When water goes from vapor to the solid state directly, it is called deposition. But in meteorology, this change is also called sublimation. Note that both of these phase changes miss out the liquid phase. Sublimation from ice to water vapor absorbs latent heat, and sublimation or deposition from water vapor to ice releases latent heat. In meteorology, an instrument called a hygrometer or psychrometer is used to measure the amount of moisture in the atmosphere. Traditionally, these instruments have a wet bulb and a dry bulb thermometer. The wet bulb thermometer is wrapped in a moist muslin cloth. If the surrounding air is unsaturated, water will evaporate from the muslin. Latent heat will be absorbed from the thermometer and stored in the water vapor. This lowers the temperature of the wet bulb. If the air is saturated, no evaporation will take place, and the wet bulb temperature and dry bulb temperature will be the same. Using a scale found on the instrument, the difference between the two thermometers gives a measure of the amount of moisture held in the atmosphere, usually expressed as a relative humidity. Relative humidity is the amount of water vapor a body of air actually contains, expressed as a percentage of the maximum amount it could hold. If the air is holding as much as it can, then we will have a relative humidity of 100%, that is saturation. If the air is holding only half the amount of water vapor it could actually hold, then the relative humidity would be 50%. The temperature where the relative humidity reaches 100%, that is the temperature at which saturation occurs, is known as the dew point temperature. Shown here is a parcel of air which is at 15 degrees Celsius and has a certain amount of water vapor inside. You will recall that when we cool air down, we reduce its capacity to hold water vapor. Look at the image and notice that when we cool the parcel of air, its capacity to hold water vapor reduces, and the relative amount of moisture in the parcel of air increases. In other words, its relative humidity is increasing. When 10 degrees Celsius is reached, notice that now the parcel of air is holding as much water vapor as it can and is therefore saturated. The relative humidity is now 100%. This temperature is the dew point temperature. If the parcel of air were to cool further, condensation would occur because the air can hold no more water vapor at this temperature. This condensation is visible to us because clouds and fog will form as visible water droplets condense out of the saturated air. This completes the lesson on humidity. The information you have learnt is vital to our understanding of clouds and precipitation. An understanding of the dew point temperature is especially important. However, this will be covered later in the lesson on clouds. The concept of relative humidity is also very important and will be mentioned many times in the context of other lessons.